With 25G becoming mainstream, the industry is already looking forward to the next dominant line rate, 56 gigabits per second. Recent decisions in the IEEE have made clear that PAM4, or pulse amplitude modulation, will be the path forward for Ethernet. While the industry is still preparing for PAM4, Xilinx is leading the way. The Xilinx SerDes engineering team has developed a 56 gig PAM4 transceiver test chip in 16nm FinFET Plus. In this video, we'll show you a hardware demonstration of the technology internally developed by Xilinx that will be available when the industry is ready to move to PAM4. The platform consists of the evaluation board for the test chip, with an FPGA development board being used for control. PRBS pattern generators and checkers located on the test chip are being used for all of the testing we are showing today. As with any functional transceiver, there are two sides to this puzzle: the transmitter and the receiver, both of which are up and running here in hardware. The eye diagram shows us the primary difference between a standard NRZ implementation and how PAM4 carries information. You can see the use of 4 voltage levels instead of the traditional 2 for NRZ allows twice as many bits per second at a particular baud rate. It's quite a change from the one big eye we're all used to seeing. Also note that our transmitter has great linearity. This is one of the many new challenges of PAM4 SerDes design that our engineering team has already conquered. We also have the same sorts of tools to compensate channel loss, transmitter pre- and post-emphasis, with very similar impact to the transmitter eye. So, why is the industry moving to PAM4? Well, briefly, it's channel loss. Channel loss is why PAM4 becomes necessary to achieve 50 gig plus data rates, given the current industry standard channels. With 2 bits per UI, the Nyquist frequency is the same as if we were running at 28 gigabits per second NRZ. This means twice as much data over the same channels that are being used today for 28 gigabits per second. The trade-offs are in the height of each eye, losing about 9 dB by splitting one eye in NRZ into 3 in PAM4, and the complexity of the transmitter and especially the receiver. With the transmitter eye looking good, let's take a look at the receiver. As there are now 4 distinct levels that need to be recovered to accurately receive data, it becomes much more challenging to repair the incoming signal degradation due to channel impairments. Fortunately, the equalization in this device is up to the task. We are transmitting PRBS31 across 28 plus dB of copper and are recovering the data through the receiver. To give you an idea of the margin, we have generated a scan of the received data before and after equalization. You can distinctly see the 4 levels we need to receive data. With this test chip built on TSMC's 16nm FinFET Plus technology, we have shown you that Xilinx is well equipped for monolithic integration of the most advanced 56G SerDes. For more information on the UltraScale Plus transceiver portfolio, please visit xilinx.com/transceivers. Thank you.